Okay, so I'm going to go through now building up a real, I'm doing air quotes, you can't see them, a real parser in JavaScript. The reason I'm doing this outside a parser generator and a LexA is to actually show that this is something you can build yourself, but you probably just don't want to. So the plan here is we're just going to develop a grammar for mathematical expressions. We're going to create something that can parse those expressions, and then to show there's actually a point to this, we're actually going to do evaluation of expressions, differentiation, and actually a few lectures on we're going to look at turning these into instructions. So the approach I'm going to use is a first principles approach. So we're not going to use a LexA or a parser generator. I don't recommend that you actually do this unless you absolutely have to, but it is a way that you can actually create parsers. So either something very simple can be done in this way, or actually something very complicated. So here is the grammar we're going to work with. I've got various things going on here. That sort of works better. Whatever. So we've got an expression can be defined as term plus expression, term minus expression, and an expression can also be a bracketed expression as a factor. We've got things like factors, which can appear as part of a term, so a factor times a term, a factor divided by a term, or just a factor. So we've got various non-terminals like factor, x per term. We've also got some terminal tokens. So I would say these things are actual tokens because they're not composite structural things. They can be matched by a regular expression. We've got the true character literals, which are all of these type things, or if we go up to a full character class if we wanted to. So there are all these kinds of characters that can appear in the tokens themselves. So one of the things we can do is to actually refactor this grammar. So here is my original grammar, and I'm not really distinguishing between non-terminals and these regular terminals. So here I've made it much more explicit. Expert, term, and factor are non-terminals because they are composite. They are built up in terms of other non-terminals and terminals. Things like an identifier, a number, even a character, these are things that can be matched by regular expressions. So I'm going to say that these things are actually tokens. So I got things like an identifier token, a number token, and some sort of literal tokens. So first thing we need to do is actually create a LexA that's going to split this thing up, and that LexA needs to be defined in terms of regular expressions. So I can come in and find some things like a sequence of decimal digits seems like it should be a token. So if I try that, I get some things like 50 and 60 and 100, which is fine, but A123 should not be a number. That should actually be an identifier because it starts with a character. If I try for identifiers, I have similar kinds of problems that like X, fine, it's an identifier, ZZ, fine. But again, A123 shouldn't be the entire identifier. The entire identifier should be A123. So looking back at my grammar, I could be more careful and say an identifier is a character followed by 0 or more characters and digits. So actually what I want is there must be a character, and there optionally, or there will appear 0 or more of these things. So the actual nesting here, remember, looks something like this. So now I've got all of my identifiers. You might wonder, why am I not recognizing this? And that's because according to my grammar, it's only lowercase. So this is actually not a legal token in my parser. So if I simplify that down, that's one of the things that I could match. Let's wrap that in brackets. Another thing that I could match would be the numbers. And now I can get these tokens as well. Other things that could match would be all of my other things like brackets, times, plus, anything else, equals, oops. So this is now a tokenizer that's recognizing everything except for this illegal stuff. I could actually go a little bit further and say, well, what about white space? White space is a token, why not? I could be more precise and say something like that. So now I've got a set of regular expressions separated by these pipes, which are going to match any of these valid tokens, and they actually reject the invalid things. So Lexing is all about regular expressions, and tokens must be described as regular expressions. So the association we have in our LexA is the left-hand side is a regular expression, the right-hand side is whatever we want the high-level token to be. So a lot of the time we'll try and split these things up such that only one can possibly match. Sometimes the listed order is important, so there'll be a precedence that you'll try this, then you try this, then you try this. But this is a definition of the tokens in my system. Here is exactly the same information, except now I've actually done it as a data structure. So this is done in JavaScript, so I have this overarching list, and then within this I have lots and lots of these pairs. So each pair is a regular expression and the kind of token it matches to. And this is just following my mapping here. At the end I have this thing T error, which is saying that anything else that you see is actually an error. So this is just a data structure representing my tokens. Here is my actual LexA. I call it a LexA. I could call it a finite state automata. So the LexA is going to take in a string, and what it's going to produce is a sequence of tokens. So while there is something left inside the string, the first thing it will do is trim any leading white space. So this trim function will take any white space characters off the beginning or the end and return the trimmed string. So now source starts with a non-white space character. So this loop is going to consider each one of the patterns in my data structure. So it's going to go through each one of these. For each of those rules, which is a single element, for example this, it will try to match rule 0, which will be the regular expression over this side. If it matches, then it will return the token type as whatever's on the right hand side, so one of these things. And the value of that token will be this matches thing. This is something that actually comes out of our regular expression engine. So I am relying on some stuff. I'm actually relying on the regular expression matcher in JavaScript. If we find something, we break because we found it. Otherwise, we go back to the beginning and keep on trying. We're actually guaranteed in this that there's this catch-all rule at the end that if we go through all of this, then it will just say error because there's no more tokens that could match. Once it's found something, first thing it does is actually consume those characters off the beginning of the string, and then it pushes the token type onto the back of the output, and then that's our tokens. So if I take this code, I mean this is just exactly the code. Here is an example of a string that I want to actually turn into tokens. It calls my LexA function and then just prints out all the tokens. If I run that, I get an ID because I've got that, I get a left, I get a right, I get a identifier, and a plus. Note if I do something like this, you might wonder, well, is this an identifier, is it a number? It's clearly not legal, it doesn't make any sense, but from a lexical point of view, it simply appears as this is a number, this is an identifier. The LexA doesn't care, because the LexA doesn't care what tokens happen next to each other. The parser will care about that a lot, but in the LexA we don't mind. So this has only given us the actual token types themselves, so the set of tokens from our finite set of tokens that the PDA is going to match. So some of these ones actually need attributes. So the identifier, what was the name of that attribute? the number. What was the number associated with that attribute? Note that these are not going to affect the way that we parse, but they are going to be needed once we parsed. So when you're doing code generation, you're going to need to know what was the name and what was the number. Other ones of these, it doesn't matter at all. So if you look at the token t-left, it is t-left. You know that it must be matched with a left open brackets. So these things called synthesized attributes are derived from the child tokens. So they're actually built up from the sort of terminals and then potentially up through the non-terminals, and they're derived upwards towards the top of the tree. So a general approach is to say for a production or non-terminal x, x.a is the value of attribute a on production x. So in this case we're going to say that something of TID has a raw attribute, and that's the string representing the attribute. A number has a raw attribute, which is the actual number, and these ones have a rather boring attribute, which is just brackets or pluses. Okay, so I'm actually doing this in JavaScript. Python also has similar abilities. I can actually, how do I do JavaScript console? There's lots of stuff going wrong there. So JavaScript has things like arrays. I can say x equals that, and if I print x back out, I can say x1 equals 1, and then if I print x, it has some sort of slightly strange behavior. And I can say x equals 5, and if I then ask for the value, it comes back with 5, and I can also index him with 1, and I get back my 1. So JavaScript is a bit weird. I probably shouldn't print those things out because they make no sense. But basically, an array is actually a kind of dictionary, and I can look up things in here by anything that has a unique value. It's a bit like, you can think of it as a hash table. So anything that's uniquely hashable and comparable, I can put in here. It also has things like, if I say y equals an object, I can say y dot equals something. Oops, a number. And if I then print y, it's an object that has the property that. So I'll occasionally use these things to actually make the code easier to look at. How do I shut you now? I don't know. I cannot get rid of that. Oh, yes, there we go. Okay, so I'm just going to use these things where I can do maps, where I can look things up with any key I feel like. So in order to support attributes, I'm going to create this helper function called makeToken, which takes the type of the token and the raw value of the token. And all it's going to return is an object that has a property called type and a property called raw. And down here, rather than just pushing on the type, I push on the token type and the token value. So all this is doing is saying that the tokens are going to be objects with a type field and a raw field. I can then, if I want to run this thing again, I'm going to grab that thing from earlier. So if I take that, put it down here, let's put it up there. I wonder what happens if I run that. Object, 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 object. So if I do dot type, then I get that, and if I do dot raw, I get that. HTML is weird. Okay, never mind.